This is Lesson 1, 3.7, Implicit Differentiation. This is a new concept. We're going to start off with an introduction. So consider the expression 2f of x minus 5f cubed x. You might say f of x to the power of 3 plus x to the power of 7 minus 1. What I'm going to ask you to do here is to take the derivative of this expression. So let's see, we would have 2 times the derivative of f, which would be, f prime of x. Then we come over here and we have 5 stuffed to the power of 3. So I'm going to bring down the 3, multiply it to the 5. So we have 15 stuff to the power of 2 times the derivative of the stuff plus 7x to the power of 6. So we've done this before, and that should have been pretty straightforward. Let's take a look at the second one. In this case, I'm going to have 5x to the power of 2 minus x cubed times f of x plus f of x to the power of 4. And again, we're going to find the derivative of this. This is sort of a warm-up. You should be able to do this at this point. Press pause and then check your answer. So here we go. We have 10x minus, now we have a product here. One way to do this is to keep the negative out front and then do the derivative of the product. So we would have x cubed times f prime of x, first term times the derivative of the second, plus second term times the derivative of the first. See, and then we had to put that in parentheses because the minus applies to both parts. Then we have plus, and we employ the chain rule again, 4 stuff to the power of 3 times the derivative of stuff. That's one way to do the problem. I want to show you another way, the way that I like to do it. We would say here again 10x for the first term, and then I would treat the minus x cubed as if it's plus a negative x cubed. So that would lead me to first term would be negative x cubed times the derivative of the second, f prime of x, plus second term, f of x, times the derivative of the first, and that would be a negative 3x squared. Then I continue on, 4 stuff cubed times the derivative of the stuff. And you see it's the same, the only difference is I didn't have to distribute in the second way because it was already done for me. That was example 2. Let's move on here. Number 3 is that expression here. We're going to find the derivative. Please avoid the quotient rule. So the last term we would write f of x to the power of negative 1. So the derivative of 5 is 0. Again, we have the product rule. So negative x times f prime of x, first term times the derivative of the second, plus second term, f of x times the derivative of the first, which is negative 1. And then over here, again, this is f of x to the negative 1 power. So I'm going to bring down the negative 1, and that's going to combine with this negative to make it plus f of x to the power of negative 2 times the derivative of the stuff, f prime of x. Okay, let's take a look at the next one. In this one, it's going to be a little bit different. Let me write the expression here. 5x to the power of 7 f of x to the power of 4 minus f of x equals 2. So this is different because it's an equation. So the goal in this here is to find f prime of x. We're actually going to solve for f prime of x. But before we do that, I want to come over here in the margin. Suppose that I had x minus 1 to the power of 2 over 3 plus 4 equals 10. Now, if you were solving this back in algebra, you would subtract both sides by 4, but I wouldn't show that. I would say x minus 1 squared over 3 equals 6. I would just do it. So I had this row, and then I'd have the next row. And then after that, I would multiply both sides. I wouldn't show anything. I would just do it. I'd multiply both sides by 3. In the next step, I would take the square root of both sides, and that would give me plus minus the square root 18. And then the last step, I'd add 1. So 1 plus minus square root 18. So the reason I show you that is we're pretty comfortable. You should be comfortable with doing that. Some people do this and try to think, well, this is wrong. They write equals, 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 equals. And that is technically wrong if you're reading it. That would imply that this here is equal to the 10, which it's not, and so on and so forth. It would imply that this here equals 18, which it is not. So we don't write equals, equals, equals every time. We just go line by line by line doing the operations. So that's going to be true over here when we try to find f prime of x. So first thing I'm going to do is take the derivative of both sides of the equation. So I'm going to write it out and then show prime that I'm going to do the derivative of both sides. Let's do it. So we do have a product here. So first term times the derivative of the second. 4 stuff to the power of 3 times the derivative of the stuff plus second term times the derivative of the first, 35x to the power of 6 minus, and then we have f prime of x, and then that equals the derivative of 2, which is 0. Again, the ultimate goal is to solve for f prime of x. So what I want to do is I want to look at the terms with an f prime in it, and I want to factor out an f prime from those terms. So when I factor it out, that's going to leave me with 20 x to the power of 7 f cubed x. That factored out of that term. Now when I factor out of this term, it's a minus 1. See, but now I still have this here, and this does not have f prime of x in it. So I want to bring that to the other side via, in this case, subtraction. So minus 35 x to the power of 6 f4, or f to the 4th x, like that. And then in my final step, f prime of x equals negative 35 x to the power of 6 f4th x all over this entire quantity, 20x to the 7th f cubed x minus 1. Just like that. So example number 5 is another equation, and you're also going to solve for f prime of x. So I'm going to do the derivative of both sides, and I'm going to write that derivative. I suggest you press pause now. Really do. Press pause, work it out, and then check your work. Here is the first line. The product rule here will yield this answer, and the product rule here will yield this answer. And of course that will equal f prime of x, yielding this line here. So what have I done? I put all the terms that have f prime of x together on one side, so I'm circling the f prime terms. Now this one here had to be brought over to the side. That's why I have a negative f prime of x. Now it would also work if I brought them all over to the right hand side. What I did in this particular case was I took the terms that do not have f prime of x, the ones circled here in purple, and I brought them to the other side. So it's going to be minus this term and then plus this term. That's what leads me to my equation at the bottom here. So the next step is to factor out an f prime of x, and I'm left with x squared minus 3x cubed f squared x minus 1. And that, of course, is going to equal the right-hand side. The last step is to divide that quantity, like that. A couple important things. It is possible that you have these reversed, as long as the negative is in front of the 2x and the positive is in front of the 3x squared. These terms at the bottom can be rearranged as long as their terms have the right sign. You could have also had the opposite of this. Perhaps you had plus 2x f of x minus 3x squared times f cubed x. That's okay as long as all these terms at the bottom also were opposite as a sign, kind of like multiplying top and bottom by negative 1. In the second page of the packet, they ask us to do a couple things. First off, to identify some shapes. So you probably recognize this as a circle. And the second one you probably recognize as an ellipse. The third one, hyperbola. And the last one. If you don't know what the last one is, you're not alone. Nobody knows what this is. Nobody knows the shape. So what I like to do, if I have a funky shape, a funky curve or relationship that I don't know what it is, I like to call it an amoeba. Amoeba. Okay? So the thing that these all have in common, though, they're all relationships. They're not all quadratic. The thing they have in common is that they're not functions. So even though they're not functions, if we were to find dy dx, what would that represent? It's the same thing it has always represented. What does dy dx represent in all these cases, including the amoeba? What it does, dy dx gives an equation for the slope of a tangent to the curve at points x, y. So gives an equation for the slope of a tangent to the curve at points x, y. So there's not room for this in your notes, but I want to talk about why this method that we're about to do is called implicit differentiation. Let's take this circle, for instance. And suppose we solved for y. Y squared equals 1 minus x squared. Y equals plus minus the square root of 1 minus x squared. So this is not a function, it's a circle. Y equals plus minus makes it not a function. But if I looked at the positive root, 1 minus x squared, that would give me a semicircle, the upper half, and y equals negative radical, that would give me the bottom half of the circle. So we would say that the circle cannot be defined explicitly by y. It would need more than one y to complete the circle. So we say the circle can be defined implicitly. It's defined implicitly by two separate functions. One function here which I'll trace in blue, and the other which remains white. So if you had some kind of amoeba, it might not be a function, but in that amoeba there may be several functions, maybe one here and another here and yet another let's say, here. So the amoeba is made up of functions. And all those functions, if we find dy dx of all those functions, it will model the same equation. Okay, so the key to all of the problems that we're about to do, the key is to treat y like stuff, or treat y like f of x as we did in the warm-up. So let's get ready. Example 1 gives us some relationship, it gives us some amoeba that we don't necessarily know what it looks like. The first part, A, wants us to find dy dx. So what we're going to do is take the derivative of this relationship. I just changed my notation from Lagrange prime to Leibniz with the dy dx information. Okay, so again, the key to this is treat y like it's f of x. It's more than just a variable, it's a function. So we could think of this as f of x to the power 4 plus 3 times f of x. So when I find the derivative, I have 4 stuff to the power 3 times the derivative of stuff, and that's going to be times dy dx, plus 3y, so the derivative would be 3 times the derivative of y with respect to x, minus 12x squared. You could technically say dx, and that's equal to 1. And that whole thing is going to equal 5. So the algebra is just like we did in the warm-up, or the introduction. I'm going to factor out a dy dx out of the terms that it applies. And here I have to bring that over. So plus 12x squared. And lastly, dy dx equals 5 plus 12x squared over 4y cubed plus 3. That is the derivative. That is dy dx. That will give us the slope of any tangent to the amoeba. And in part B, it wants to know specifically what is the slope of the tangent at the point 1, negative 2. What is the slope of that tangent? So dy dx at the point 1, negative 2, I will plug 1 in for x, and I will plug negative 2 in for y. And that will yield a negative 17 over 29. That would be the slope of that tangent. The question does not ask for an equation of a tangent line, but we certainly know how to do that. Y minus y1, so y minus negative 2, y plus 2 equals m, negative 17/29 times the quantity x minus 1. So if it asks for equation of a tangent line, that's what we would have. So, ran out of room. So let's take a look then at part C. First, let me rewrite dy dx was 5 plus 12x squared over 4y cubed plus 3. Okay, so now in part C, it wants us to find this, d squared y dx squared. So that's the second derivative. That's the derivative of the derivative. That's the derivative of the derivative. This also explains why the notation goes d squared y. See d here and d here makes d squared, and then dx is squared kind of like that. Anyway, we're taking the derivative of the derivative. We're taking the derivative of the derivative. 5 plus 12x squared over 4y cubed plus 3. And looks like we're going to use the quotient rule. But remember, y is still a function of stuff, so, or a function of x. It is stuff. So we have bottom times the derivative of the top, which is 24x minus the top times the derivative of the bottom. Now here we go. So this is 12y squared times dy dx all over the bottom squared. Now, even if I ask you not to simplify, and I will on the test say do not simplify, the problem is still not finished. It's not a matter of simplification, but what I'm looking for, now this would probably be a 5-point part of the question. Part C would be worth 5 points, and I'm not looking that you get the correct quotient here, although it's expected. What I'm looking for is that you don't leave dy dx like that. You don't keep it expressed as dy dx. I'm looking for a final step. Because we already know what dy dx is, I'm looking to earn any of the 5 points. I'm looking that you substitute that back in as a final step. So 4y cubed plus 3 times 24x minus quantity 5 plus 12x squared times 12y squared, and then I have 5 plus 12x squared over 4y cubed plus 3 all over 4y cubed plus 3 quantity squared. So this substitution is what I'm looking for in part C. On the next page in the notes, you have these 3 examples. I really highly urge you to press pause, work them out, and then when you come back, I will have all the solutions worked out and you can check your work. So press pause now, or else you're just going to see all the solutions appear. So here's the answer to number 2. You may not have simplified as far as I did here, so you may have some extra 2's in your problem, but again, the final thing was that we substituted that back in. So I'm about to work out the second one. A couple product rules in the solution, and you will also notice that I'm using prime instead of dy dx. I'm doing that because the author of the question says find y prime. Okay, last one, gonna work it out. And here's the first step. Dy dx, because the derivative of y is dy dx, equals product rule. First term x squared. The derivative of sine stuff, sine y, would be cosine stuff, derivative of stuff. That's the dy dx. Plus second term sine y times the derivative of the first 2x. I need the dy dx's on the same side, so I'm going to subtract the x squared cosine y dy dx, and that's going to equal the 2x sine y. I'm going to come over here, factor it out. Dy dx, 1 minus x squared cosine y equals 2x sine y, and finally dy dx equals 2x sine y over 1 minus x squared cosine y. Or, like I'd stated before, maybe you had negative 2x sine y over x squared cosine y minus 1, where all the signs were changed, like a negative 1 over negative 1. This is example 5 of section 3.7. What I would like you to do is press pause to the video and see if you can solve the entire problem, and then unpause it to check your work. So here we go with the solution. I'm first going to find the derivative with respect to x of the entire relationship. Tangent of xy plus x squared y plus 2 equals x. Notice this is the tangent of stuff, and within the stuff we have to do a product rule. So here we go. The derivative, tangent stuff, is secant squared stuff. Now we're ready for the derivative of the stuff, and we have first term. And then the derivative of y with respect to x is dy dx. Remember, we treat y like it is its own stuff. Plus second term y times the derivative of x, which is 1. Plus, now we're going to do the derivative of this, also using a product rule. First term times the derivative of the second, plus second term times the derivative of the first, and then the derivative of 2 is 0, and then equals the derivative of x, which is 1. So this part, the derivative of this part, was all of this, and the derivative of this part was all of that. So now we're ready to do the algebra portion of this. If this entire problem 5 was worth 25 points, this line of information would have been worth 10. So a tricky step here is that this needs to be distributed to these two terms before we do anything else. So we have x times secant squared xy dy dx plus y times secant squared xy. Then we have plus the blue portion, x squared dy dx plus 2xy equals 1. So the goal is to isolate dy dx. So I'm going to factor dy dx out of x secant squared xy. See, this term has a dy dx in it, and this is the other term that has it. So plus x squared. And then I need to bring the other pieces to the other side via subtraction. So that's going to equal 1 minus 2xy minus y secant squared xy. Our last step here is to get dy dx by itself. So I'm going to divide that entire quantity to both sides and show that here, divided by that. So that's dy dx. But the problem wants us to find an equation of the tangent to the curve at the point when y equals 0. So the next thing we have to do is figure out what the point is on the curve. I like to call this the amoeba because I don't know what it looks like. So I have to find a point on the amoeba when y equals 0. So if y equals 0, I'm going to substitute in the amoeba. So I have the tangent of 0 plus 0 plus 2 equals x. And the tangent of 0 is 0, so that is going to lead me to x equals 2. And the point then is 2, 0. Again, if this were a 25-point question, the light blue here analysis leading to the point 2, 0 would be worth 5 points. The algebra down here would also be worth 5 points. So the last 5 points then is finding the equation of the tangent line. So I need dy dx at the point 2, 0. So I'm going to plug that into my derivative, where 2 is for x and 0 is for y. And if you do all that, it comes out to be 1 minus 0 minus 0 over, let's see, 2 times 1 plus 4. So the slope comes out to be 1/6. And we're ready to write the equation of the tangent line. Y minus 0 equals 1/6 x minus 2. And there it is. That is the final answer to the question.